Hey there, STEM Chemistry. This is Ms. Ruark. This is Vodcast 5.5, where we're going to learn how to determine if a double replacement reaction has actually happened and how to use the solubility rules to determine that. So, all right, let's review ions again real quick. We know that an ionic compound means that it is ionic. It has ions in it. It's a salt. That's another way of saying it. And it refers to a positive ion and a negative ion. Okay, just to review, positive means we have a cation and a negative means we have an anion. Okay, or a metal and a nonmetal. Okay, so usually this is a metal and a nonmetal or a metal and a polyatomic ion. All right, dissolve. So what in the world does this really mean? Well, for salts, it means that the ions have dissociated. So the ions have dissociated. What does that mean? Well, that means that they've broken apart. They're not together anymore. So NaCl, Aq, is the same thing as having Na, or sodium ions, and chlorine ions. Okay? They're still near each other. They've just broken apart when you put them into water. Okay? So acids will form ions. You'll end up with your hydrogen ion, and you'll have your chlorine ions floating around in solution. And for bases, you would have your sodium ions floating in solution, and you would have your hydroxide ions floating around in solution. Now, typically I would show this hydration animation, but when you come to class, I'm going to show it to make a little bit more sense, but let's go back to this. What happens is you have your water, and then you have your sodium ions and your chlorine ions, and the water, actually the negative aspect of the water surrounds itself around the sodium, and the positive aspect of the water surrounds itself around the chlorine, and that's what we call hydration. Okay, so how is charge determined? So the number of valence electrons is the charge, or sorry, the number of valence electrons helps determine the charge. So, for example, fluorine and chlorine, or any of the halogens, are going to gain one electron in order to be just like the noble gases, and so they form a -1 charge and a -1 charge for the fluorine and the chlorine. All right, calcium is going to lose 2 electrons, and then that way it's going to form a +2 charge. This is all review. You guys know this. Okay. Practice writing ions from formulas. So write the ions that would be formed from this. So this would break down into sodium, oops, not a +2, positive, Aq, and carbonate, -2, Aq. All right. What are the ions for calcium phosphate? Well, that breaks down into 3 calcium ions. I should probably write let's balance them out. 3 calcium ions, aqueous, and 2 phosphate ions, aqueous. And then cadmium nitrate breaks down into 1 cadmium +2 aqueous and 2 nitrate ions, which are also aqueous. Okay, getting the hang of this, huh? Na2S breaks down into 2 sodium ions, Aq, and 1 sulfur ion, Aq. And then for the last one, we have magnesium. There should be 3 of them with a +2 charge, Aq, and borate, -3. Oops, Aq. Okay. It's easy, right? Piece of cake. Okay, well, let's use that to apply it. So here are our solubility rules. Oops, go back. Okay, how does that work? Well, let me go back to this page. We have Na2CO3, sodium carbonate, calcium phosphate. So it doesn't like me. It just really doesn't like me today. Okay, sodium carbonate, Na2CO3. What else? We have calcium phosphate, PO4 Let's say we have ammonium sulfate. I'm just pulling up some different compounds that we might come across. Lead 2 chloride. Okay, so how do we use the solubility rules? Well, this is just an example of a chart that you could have for solubility rules. Okay, so we know that you'll always start at the top of the solubility rules with rule number 1, and you'll keep going. As soon as you hit a rule that makes it tells you that it's soluble or not soluble, you stop. If you make it through every single one of them, you still don't know. Guess what? It's probably soluble. Okay, so salts of alkali metals and ammonia. All right, so if you have a salt of an alkali metal, meaning a group 1 metal, or ammonia, so if you have an alkali metal or ammonia at the beginning, it's going to be soluble. What does soluble mean? Soluble means that it dissolves. That means it's going to be aqueous. If it's insoluble or slightly soluble, it's going to be the same thing. It means it's not going to dissolve, and we say it's a solid. All right, so if on this first one we have sodium carbonate, guess what? It has a group 1 metal here. So guess this is going to break apart. It is soluble into your ions and carbonate. It will break apart. Why? Because of that group 1 metal. Okay, on this next one, calcium phosphate, salts of alkali metals and ammonia. Nope, doesn't work. Nitrate salts or chlorate salts. So if you have nitrate or chlorate at the end, it's going to be soluble, but we don't have that. We have a phosphate. All right, sulfate salts accept common compounds with lead, silver, mercury. We call those the 3 horsemen. They're awesome. And then barium, strontium, and calcium. Those are the 3 other bad ones. All right, we don't have either one of those. All right, chloride salts, it's not a chloride, it's a phosphate. Carbonates, phosphates, and chromates, sulfides, and hydroxides are going to be insoluble. So guess what? This is not going to break apart. See how I did that? Now, if this had been sodium or a group 1 metal, it would break apart. Okay, NH42SO4, salts of alkali metals and ammonia. It has ammonium. This should say ammonium, not ammonia. All right, so this will break apart. This will be aqueous. It will break apart. All you have to do is put the AQ after it. Really, you don't have to break it apart, but I'm breaking it apart so you guys can see what's going on here. And then SO4 with a 2 minus AQ. All right, lead 2 chloride. Is it an alkali metal or ammonium? No. Is it a nitrate or a chlorate? No, it's a chloride. Is it a sulfate? No. Chloride salts. It is a chloride salt, except it is soluble unless it's silver, lead, or mercury, the 3 horsemen, right? It has lead, so it's going to be a solid. It will not break apart. Okay, so this is how you would use this. Now, what I want you to do is I want you to take this little chart here. If you don't have it in your notes, I think it is, but if it's not in your notes, then I want you to find it in your textbook, because it's not this table, but it's one that's similar to this, or copy this down because you're going to need it on the next slide. All right, on the next slide, here we go. Here we are. It says circle the compounds that are insoluble. So what I want you to do is circle the ones that are not soluble, okay, according to the rules. And I'm going to circle these also, but I'm going to pause it, and I want you guys to try it on your own, and then you're going to come back and check your work. Okay, pause. Okay, so circling the compounds that will be insoluble according to the solubility rules, and that wasn't supposed to happen. My pen just doesn't like me today. Okay, this one is going to be soluble. This one is soluble. This one is soluble because of the ammonium. This is a sulfate, and the sulfates are soluble unless it has the 3 horsemen, and this is not a 3 horsemen. Let's see, this one is solid because it is a hydroxide. Okay, this one is not. This one's going to be insoluble because it has silver attached to the chlorine. Cadmium sulfide, the sulfide makes it insoluble. This one's okay. The sulfate, because it's attached to the lead, it is, these should be circled, sorry, not underlined. Haha. Barium hydroxide would be a solid. This one is not. 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 This one is a solid. This one is not. I think that's all we've got. Okay. According to our solubility rules, that's what we have there. And, okay. There we go. I thought that would be kind of funny. So that gives you a little bit of practice with that. We'll come into class and we'll do some more practice on determining whether something's soluble or not. I'll see you then.